Meta. Skin facade. We don't just know facades, we define them. A dedicated platform for the art and science of building envelopes and architectural skins. With over 2 decades of hands-on experience, we bring you practical insights, technical expertise, and the latest innovations in facade design and execution. Chapter 3. Orientation as a wind boundary condition for facade design. Orientation as a wind boundary condition for facade design. In the previous episode, we discussed thermodynamics of facades, how orientation affects heat flow and solar gain. In this episode, we shift from heat to wind. Orientation as wind boundary. How building rotation fundamentally changes wind-facade interaction. Flow physics. Understanding pressure, suction, and separation at the building envelope. Design strategy. From theoretical coefficients to practical facade detailing and zoning. Designing with the wind. In this episode, wind as a flow phenomenon rather than a simple uniform load. Orientation does not change wind climate, but it fundamentally changes how wind interacts with the facade. Wind is not a static load, it is a dynamic fluid interacting with built form. While wind climate is determined by geography, meteorology, and exposure category, facade design is governed by how wind flows around a building. Orientation does not change the wind climate at a site, but it fundamentally changes the distribution of pressure and suction across facade surfaces. The same wind, acting on the same building at the same site, produces entirely different force distributions when orientation shifts. Orientation defines where wind stagnates, where flow separates, and where suction governs structural and envelope design. Orientation is a boundary condition for wind interaction, not a secondary parameter. It matters not because wind is constant, but because facade design is governed by the worst directional response under code-prescribed extreme conditions. Wind as flow. The physics behind facade. Loads. Wind is dynamic, not uniform. Accelerates. Wind speed increases around building corners and edges, creating localized high-velocity zones that amplify negative pressures and suction. Decelerates. As wind impacts the windward facade, velocity drops and kinetic energy converts to pressure. This is the stagnation zone with positive pressure coefficients. Separates. At sharp edges, corners, and roof lines, flow detaches from the building surface, creating low-pressure wake regions and high suction loads. Reattaches. Downstream of separation zones, flow may reattach to leeward surfaces, producing complex pressure distributions that vary with building geometry and aspect ratio. Variable wind. Direction versus design. Logic. Wind. Climate versus design. Wind direction varies continuously from 0°D to 360°N on an hourly, daily, and seasonal basis. However, facade design is not based on average or prevailing wind conditions. Instead, we design for the most adverse directional response, which produces the highest pressures and suctions on critical facade zones. The wind rose diagram illustrates the directional distribution of wind frequency at the site, showing how often wind approaches from different compass sectors. The highlighted arrow represents the extreme, design-governing wind direction, which may not be the most frequent direction, but produces the highest facade pressures and suctions according to code provisions and site-specific exposure. Facade design is governed by this extreme wind, not by dominant frequency. Building orientation determines which facades, edges, and corners are exposed to this critical direction. Wind varies, 0°D 360°, hourly and seasonal fluctuations across all compass directions. Design based on extremes. Worst-case directional response per code provisions. IS 875, ASA 7, EN 1991. Pressure coefficient, CP. The language of wind on facades. Understanding CP as a non-dimensional parameter. The pressure coefficient, CP, is the most critical concept in wind engineering for building envelopes. CP is a non-dimensional parameter that describes how wind interacts with a surface, independent of building size, material properties, or absolute wind speed. It tells us the behavior of wind on a surface rather than the load directly. The fundamental relationship. CP Shakers, PL Sau, Viakors 2. Where P is the local pressure at the facade surface, RHO is air density, and V is the reference wind velocity. This expression normalizes pressure relative to the dynamic pressure of the approaching wind flow. CPR0 indicates positive pressure, stagnation. Wind is decelerating and pushing onto the facade surface. Windward stagnation zones where kinetic energy converts to pressure. CPR0 indicates suction, flow separation. Wind has detached and is pulling away from the facade. Leeward, side, and corner zones where flow separation creates negative pressure. CEP explains why loads vary across the facade and provides the theoretical foundation for zone-based design pressures. Engineering reality, orientation controls where positive and negative CP zones occur on the building envelope. The same building rotated 45 degrees will exhibit entirely different CP distributions, even under identical wind climate conditions. Pressure coefficient, CP. Zone logic in facade design. Field, standard. Zones. Lower, uniform CP.edge zones. Increased suction. Corner zones. Highest negative CP. This zoning exists because flow separation and CP variation are driven by orientation and geometry. Height. Effect and top zones. Higher wind. Higher suction. Higher kPa at top floors. Wind speed increases with height and shielding reduces. Top floors and roof-adjacent zones often govern design, CP. kPa, facade engineer's work. Facade engineer workflow, CP, pressure. Zones, plus height, FOS, factor of safety. Facade engineers convert CP into usable kPa loads, applying height factors, zoning, and safety margins. Contractor versus facade engineer's view. Contractor sees kPa, standard, corner, and different loads by levels. Engineer sees physics.cp, converted, kPa, issued to contractors. CP distribution. Depends on orientation. Plan view. How rotation redistributes wind loads. For the same building geometry under the same wind climate, rotating the building orientation produces fundamentally different CP patterns across facade surfaces. Peak pressure and suction zones shift location, magnitude, and extent depending on how the building is positioned relative to the design wind direction. D-wind, normal. Windward, plus CP, SAW 0.6 to plus 0.9. Leeward, CP area 3 to 0.6 side facades. CP area 6 to 0.8 corners. CP area 1 or to 5 out of their wind, shifted peak suction. Peak suction shifts to oblique corners. Extended edge zones experience elevated negative SEP windward area reduces. Side suction zones enlarge. Ordig wind. Different critical facade. Different critical facade. Long facades now in parallel flow with distributed suction. Previous windward-leeward distinction no longer applies. New governing corner emerges. Engineering principle. For the same building, rotating orientation changes where peak suction and pressure occur. CP peaks do not happen simultaneously on all facades. Each wind direction produces a unique load case that must be enveloped in design. Facade design is governed by extremes, not frequency. Why suction governs? Facade design. Negative CP exceeds positive CP. In facade engineering, suction loads typically exceed pressure loads and therefore govern the design of structural systems, anchors, and cladding attachments. While positive pressure on windward facades is important, the magnitude of negative pressure coefficients, especially at corners, edges, and roof perimeters, is consistently higher and drives critical design decisions. What suction governs? Anchor tension capacity. Pull-out resistance of mechanical and chemical anchors embedded in structural backup. Bracket and connection design. Tension forces in transom clips, mullion brackets, and edge support systems. Mullion and transom demand. Bending moments and deflection limits under outward acting suction loads. Panel edge retention. gasket pressure, zipper engagement, and fastener spacing at vision and spandrel glass edges. Suction is highest at corners, edges, and top levels. Zones where flow separation is most severe, and CP values reach 1.5 or lower in extreme cases. These are the governing zones for facade system capacity and performance verification. 5. 2.0x field. CP. Corner. Amplification. Corner CP typically 1.5 to 2.0 times field. CP due to flow separation. 1.5 peak. Suction. Top corner. CP values often reach 1.5 or lower in high-rise buildings. Orientation in practice. Engineering roles and real constraints. Facade. Engineer's early design role. At the concept and master planning stages, facade engineers study wind climate, exposure categories, and building massing to identify orientation-sensitive facades and critical suction zones. Early involvement allows the engineering team to flag high-risk corners and edges, provide orientation guidance, and recommend strategies to minimize peak wind demands before architectural form is finalized. Ideal engineering input. Early stage. Wind code review. Analyze applicable codes. IAS 875, ASA 7, EN 1991. Statutory approval in India. IAS 875 only, and extract windrows data, extreme direction bands, and preliminary CP distributions. Orientation comparison. Compare 2 to 3 orientation schemes, highlight high-risk facades, and recommend the orientation that reduces peak suction on critical zones. Early advisory output. Deliver orientation guidance that reduces long-term facade demand, anchor count, and system cost. Practical reality. Orientation mostly fixed. In most real-world projects, building orientation is constrained by external factors beyond the facade engineer's control. Site access and road alignment. Plot boundaries and setback regulations. FAR, floor area ratio. Optimization. Planning authority requirements. Solar access and view corridors. Urban design guidelines. Design adaptation strategy. When orientation cannot change, the focus shifts from optimization to safe resistance. Facade engineers envelop worst-case CP from all wind directions, strengthen critical zones with increased anchor density or section capacity, and optimize detailing instead of massing. Orientation becomes a fixed boundary condition, and the design adapts accordingly. Orientation drives. Facade strategy. Same building. Same wind climate. Different governing responses. The table below illustrates how orientation fundamentally changes the governing wind behavior, load distribution, and design strategy for an identical building under the same wind climate. Each orientation produces a unique set of critical zones, failure modes, and required detailing strategies. Aspect. Wind approach. Orientation. A normal to facade. Orientation. B oblique. 30° 45 fire. Orientation C parallel to long facade. Aspect. Governing behavior. Orientation. A peak suction at top corners. Orientation B extended suction along top edge. Orientation C distributed suction over large area. Aspect. Dominant CP effect. Orientation. A high CP at corners. Orientation. B moderate CP over edge zone. Orientation. C lower CP acting on many panels. Aspect. Governing risk. Orientation. A localized anchor bracket failures. Orientation B line type edge failures. Orientation C cumulative system. Demand. Aspect. Design control. Strategy. Orientation. A corner reinforcement. Increased anchor capacity, reduced spacing. Orientation. B edge stiffening. Heavier mullions, continuous dot, support. Orientation. C anchor. Density increase across entire facade. Aspect. Design, intent, orientation. A resist peak, localized forces at critical points. Orientation. B control. Edge separation and maintain. Continuity. Orientation. C share load efficiently across distributed system. Summary. Orientation optimization is ideal when design freedom exists. When orientation is fixed, as it usually is in practice, Facade engineering ensures safety, performance, and constructability through strategic detailing, zoning, and reinforcement. Orientation does not remove wind demand. It redistributes it. Facade design adapts by changing where and how resistance is provided. In the next episode, sound transmission and noise control in facade design.